All right, I'm going to give you one more look at the data that we're going to take. So you notice I have symbols for each one. All right, all good. All right, you could just pause the video and take this down if you wanted to. All right, the students are going to use little d over t to get the speed of the water in the bottle, V in the bottle. They're going to use area of the bottle, velocity of the bottle to get the flow rate in the bottle. They're going to solve these two projectile motion equations from physics 1, or whatever their previous physics was, to get the speed that the water comes out of the hole. Then they're going to use the area of the hole, the velocity of the hole to get the flow rate of the hole and see if they're both the same. That's what they're going to do. All right, all good. Here's another version of the same lab. This is called an H2O blaster. It appears at Dollar Tree between the months of about March and September as a summer toy. You'll notice all it is, it's just a big syringe with a nozzle at the end. So what I have the students do is they'll go outside, I'll bring out a big bucket of water. So what they're going to do is they're going to use a caliper to get the diameter, really ultimately the area of this little nozzle, get that area. They're also going to use the same caliper to get the area of this barrel. The plastic of the barrel is very, very thin. So I assume that the outside radius and diameter is the same thing as the inside radius and the diameter. Okay, so you get the cross-sectional areas, area of the barrel and the area of the nozzle. Okay, they're going to go outside. They're going to suck up water out of the bucket I give them. Then they're going to stand with the person who's shooting is going to shoot horizontally. We need to get the H that the water comes out as a projectile. We're going to shoot the water out at a constant rate. Somebody is going to time how long it takes to do this. How much time is that? And someone else is going to measure the distance that the water shoots out. Okay, so what do we get? Time how long it takes to squirt all the water out. Measure the distance d that the piston moves. The distance from here to here. All right. The height that the water becomes a projectile, the horizontal distance that the water shoots is a projectile, and we have both the area of the nozzle and the area of the barrel. That's what we want. So, so once again, you're going to do the exact same procedure. Little distance over time gets you the velocity of water in the barrel of the syringe. Area barrel times velocity barrel, flow rate in the barrel. Using projectile motion again, just the same as before, we can get the velocity of water coming out of the nozzle, area of the nozzle, velocity of the nozzle, flow rate of the nozzle, and you can see if those two A times V's are the same. Okay, here's an advanced version with the bottle. Ask the students to take different data of multiple trials using different size holes. So in other words, what you can do is you can buy different radius nails, heat them up one at a time with the Bunsen burner, and then poke the holes. I would poke them all at the same height, but just poke a small, poke a medium, poke a large, poke a very large. Cover them up, each with duct tape. Take off one piece of duct tape for each trial. So it's the same procedure, but we're taking data of multiple trials using different sized holes. We're going to use duct tape to cover the holes not being used. Ask the students to take, or you could ask the students to take the data while two or more holes are unplugged at the same time. Can they show the area times velocity in the barrel is the sum of area times velocities of the two holes? Can they show that? Ask an extension question such as, how does the size of the hole affect the speed at which the water emerges from the hole? The answer is it actually shouldn't, except there is such a thing as viscosity. So you can have them try the different holes of different sizes, and they can show that the velocity of water, as long as all the holes are the same height and the water level starts at the same height, the velocity coming out of the holes is the same regardless of the diameter of the hole. And that's a good transition to the Bernoulli principle, which is what we're going to talk about next. Okay, so I hope you enjoyed this discussion of continuity, and I'll see you on part C for the Bernoulli. All right, see you then.